Now let us study some of the statistical outlier detection techniques. In statistical techniques, what we do is we first assume that the all the data objects are generated by a model or a stochastic process. So the anything which is not generated by this model is going to be an outlier. And statistical models, again, they can be either parametric or non-parametric. So in case of a parametric, the distribution and the parameters are assumed. And in case it is non-parametric, there is no a priori assumption with respect to the model. And the model itself is determined based on the input data. So in statistical techniques, we use a test called discordancy test to determine if something is a outlier. So what the discordancy test first requires is a working hypothesis, and the hypothesis such that object I belongs to the distribution F for all the points. So if the hypothesis can be retained if there is no statistically significant evidence to reject for rejection. Then the discordancy test is going to verify whether there is an object such that it is significantly large or small in relation to the distribution F. So in that case, what we see is that the object OI is likely to be an outlier. As we can see here, it depends significantly on what we have chosen as the distribution F. So for a different distribution, so the OI may not be an outlier. And we may have to find out if there is an alternate distribution, and then we can see that we can create a alternate hypothesis that there is a G, the distribution G, to which the objects really belong. So that is, we need to, it is more like a trial and error because we cannot get it right at the first time. So we can have an alternate hypothesis which says that the objects belong to distribution G. And here the G may be a variant of F only based on the parameters with the same distribution, let's say Gaussian distribution with the different parameters, or it may be a different distribution. And sometimes we need to, we cannot fit the data into a single distribution. And it is possible that many of the data that we generate do not fit into a single distribution. So in such case, a mixture of alternative distributions can be used. So here what we do is that we will create a alternate hypothesis that the objects belong to a combination of F and G. So that is some part of F and the remaining part of G. So both of them put together is one. So that is what is representing the data objects. So here again, we can use this hypothesis and determine if some data object is significantly deviating from this hypothesis. So here we may use even a slippage alternate distribution. So here, instead of taking a different distribution, the F and G being altogether different distributions, they may be same distributions but with the different parameters. So when we are using the parametric approaches for finding about an outlier, so generally what we do is that we use a probability density function. So the probability density function is going to tell us the possibility of finding where is the range or the value where we are going to find most of the data objects. So given an object, if we find that its probability density function is turning out to be very small, then it is likely that that object is an outlier. So this can be the probability density function. We may be able to get it for the normal distributions with a given mean and variance, and there we can find out the objects where the density is very small, or possibly in fact below a threshold. Then we can say that those points are representing the outliers. You can take an example. We are looking at a univariate outliers, so that is just one variable. But it is in real world we may not get this simple problems, because many times we get multidimensional information, and from which we need to find out the outlier. So let's say we got a temperature data which is 10 data points, and what we use is that we use the mu and sigma to determine whether there is an outlier. So when we calculate the mu for all these 10 numbers, we are going to get a mu of 28.61, and sigma is going to be 1.51. So we know that the mu plus 3 sigma in a normal distribution contains 99.7% of data. So if we think that anything which is beyond this range is likely to be an outlier, then we can check for each one of these values if they're falling outside this mu plus minus 3 sigma. So as we observe the values, we are seeing that there is a value 24 for which we are getting it is beyond 3 sigma. So that is, it is coming to 3 mu minus 3.04 sigma. So what it means is that it is beyond this range of 99.7% of data. So if this is our threshold, then we can say that this 24 degrees temperature must be an outlier. And we may use this 5-point box, which is the box plot with giving the 5-number summary, where we have the minimum, the lowest quartile, and then the median and the upper quartile, and then the largest non-outlier value, which is the maximum. And we can use this plot to find out if there is any outlier in the given data. So what happens is here we are again depending on the same principle. So we have used the quartiles, that is the median and then the third quartile and the first quartile, to represent the range where the significant density should be there. And we have provided, which is these points which are the max and min, which are coming from the Q1 minus 1.5 times IQR, and then Q3 plus 1.5 times IQR. So essentially, in case of a normal distribution, we are likely to find 99.3% of the objects which fit into that. This is pretty similar to the 3 sigma criteria. And we can say that anything which is outside the range of max and min is an outlier. If we have a data objects which are multivariate, then it's going to be more challenging. We need to work out either we can convert the multivariate into univariate, and then we will be able to detect. So one way we can do this conversion or the transformation is using the Mahalanobis distance. So Mahalanobis distance uses the principal component axis and gives the weightage along the axis the appropriate normalization, so that all the axes are treated get equal significance with respect to determining if some object is an outlier. So in case we get a distribution of the points which are along a particular principal axis, then it normalizes the point so that along this direction it provides for higher range compared to along this direction. So thereby it is going to help you find out for a multivariate. So here we have got only 2 dimensions, so we could visualize it easily. But in general, in an n-dimensional space, it works in a similar way. It is going to find out all the principal component axes and then standard deviation along the axis, and then it is going to determine the distance of the object, the data point, and determine if it is beyond a range to be an outlier. And we may otherwise use a chi-square statistic where we are going to determine if it is significantly different from the mean, then it is going to be an outlier. So that is, we are finding out with respect to the mean along each dimension. Sometimes we get, as we had discussed, the distribution of the data, which is cannot be represented using a single distribution, which is, as you can see here, clearly there are 2 dense regions here. So in that case, we need to create a new probability density function that is a combination of 2 density functions, and then we will be able to find out if an object is an outlier if it has getting a poor score for the probability density in both the probability density functions. So for detecting the outliers in statistical techniques, we can take 2 approaches. One is the block procedure. So here what we are treating is that we are treating them as an outlier at once. We are looking at the entire data, and then we are trying to recognize the suspect objects using some technique at once with respect to all the data. The other approach can be a consecutive or sequential procedure. So here what we do is we take an inside-out approach. We first find out an object which is least likely to be an outlier, and then we start finding the objects. If that itself turns out to be an outlier, then we take it that all the data is an outlier. So if it is not, then we find out the next most extreme object, and then we start finding out, we continue this procedure till we reach a point where we realize that everything beyond it is an outlier. We may also use a non-parametric methods for detecting the outliers. So one can be a histogram. So what we can do is that we have a data here, we have got a data of the amount of transactions in let's say retail store, and what they see is that 60% of the transactions fall in this range and 20% in this range, and let's say it is in the form of a multiple of $1,000. So 60% of the transactions are below $1,000, 20% are in the range of 1,000 to 2,000, 10% in 2,000 to 3,000, and so on. And we see that the transactions which are beyond 5,000 is 100 minus this 60, 20, 90, and then 99.8. So that leaves us with 0.2% of the transactions have an amount higher than 5,000. So if we get a new transaction, we can use this histogram to determine if it is normal or abnormal, because we may set a threshold. Again, in this case, let's say it is 0.2%. So we'll see that anything which is higher than $5,000 is likely to be an outlier. So here we have a challenge of determining what is the bin size that we should be using. If we have a too small bin size, and then we may end up with the false positives. If we have a too big bin size, it is possible that there will be false negatives, so some of the outliers will fit into the bins.